Welcome students. Now we are going to see concept of convergent sequence here. Now the main aim to introduce metric space is to study convergent sequences in a context of more general than that of classical analysis. Actually, this is the one of the aim to study the metric space, because in real analysis, or when you consider the set X as set of real numbers, then in that case we know that every convergent sequence is Cauchy sequence and every Cauchy sequence is convergent sequence. But in metric space that result is not true. It means that every Cauchy sequence need not be convergent in metric space here, because if you consider this now this set X is equal to open interval 0 to 1 with usual metric, that is d of xy is equal to now absolute value of x minus y. Then if you consider this sequence, now xn is equal to now 1 upon n plus 1, okay, where here we have n belongs to n here. Now in this case, now this sequence converges to 0, or this sequence has limit 0, but this does not belongs to now this set, that is now 0 is not member of this set here. Now remember that here now this sequence also satisfies now this condition, that is absolute value of xn minus xm is less than epsilon for all m and n greater than or equal to n. And also if you consider now this space, that is Q with usual metric Q, it means that set of all real numbers, then now this sequence xn is equal to now 1 plus 1 upon 1 factorial plus 1 upon 2 factorial plus 1 upon 3 factorial plus so on 1 upon n factorial here, where now n belongs to now n, that is set of natural numbers here. Now this sequence is now here this sequence is convergent. Actually this sequence converges to now this E, but E does not belongs to now this, because E is an irrational number here. So now this sequence is not convergent in this space, that is Q comma D, where Q is the set of rational numbers here. Now this sequence now also satisfies this condition, that is absolute value of xn minus xm is less than epsilon for all m and n greater than or equal to n here. Now we want to study the concept of convergent sequence here. So now we are going to see the definition of convergent sequence here. Then after that we are going to see some theorems on convergent sequences. So now definition of convergent sequence. Convergent sequence. Now definition. Let ordered pair x comma d be a metric space. A sequence xn in X is said to be convergent if there is a point x belongs to x such that for each epsilon greater than 0, for each epsilon greater than 0, there exists a positive integer. There exists a positive integer capital N such that now distance between xn and x is less than epsilon for all n greater than or equal to n. So this is the definition of now convergent sequence. Now when xn is convergent, then in that case for each epsilon greater than 0 we have a positive integer capital N such that distance between now xn and x is less than epsilon for all n greater than or equal to n. Now using this notation, so we can say that now xn belongs to now here this open sphere, yes, epsilon x, that is the here we write here for all n greater than or equal to n, that is now yes epsilon x is the open sphere centered on x of radius epsilon here. So for each open sphere we have here xn belongs to yes epsilon x for all n greater or equal n. So we write here, or equivalently for each open sphere yes epsilon x. Now yes epsilon x is the open sphere centered on x. There exists a positive integer capital N such that we write here xn belongs to yes epsilon x for all n greater or equal n. Now we usually symbolize this by saying that, or by writing that xn converges to x here, okay, or xn tends to x here, or we write this as limit n tends to infinity of xn is equal to x, and we express it by saying that xn approaches to x or xn converges to x. Now remember here the element x, now this is called limit of the sequence here. So you should remember this, the element x is called the limit of the sequence xn. So when given sequence is convergent, then in that case we write the limit of that sequence. So remember that if the sequence is not convergent, then it is said that sequence is divergent here. Now first theorem on convergent sequence, that is, remember that here in a metric space every convergent sequence has a unique limit. So statement of this theorem is this: theorem in a metric space every convergent sequence has a unique limit. Now to prove this, we are going to consider one sequence xn in a metric space x comma d, and we are going to take limit of that sequence as x and y. Then we are going to prove that, or we are going to show that in that case we get x is equal to y here. So to prove this, now we start by taking this sequence. So proof of this theorem is, let x comma d be a metric space, and now xn be a convergent sequence, xn be a convergent sequence in x here. Now we want to show that now this sequence has a unique limit. For that, now here we are going to consider that if this sequence has two limits, that is x and y. So we write here, let if possible the sequence xn converge to two points x and y here, x and y. Then by using definition of convergent sequence, we write here, then for each epsilon greater than 0, there exist positive integers n1 and n2 such that now when xn converges to x, then in that case we can write now distance between xn and x is less than epsilon by 2 for all n greater equal n1, and when xn has limit y, then we write distance between now xn and y, now this is less than epsilon by 2 for all n greater than or equal to n2. Now here we take n is equal to now maximum value of n1 and n2 here. Now taking n is equal to now maximum value of n1 and n2, that is we take these values n1 and n2 and we consider the maximum value now among them and we take that value as n here. So therefore we can write here distance between xn and x is less than epsilon by 2 for all n greater equal capital N, say this as 1, and here distance between now xn and y, this is less than epsilon by 2 for all n greater equal n, for all n greater equal capital N. Now by using triangle inequality, now by using triangle inequality, we write here distance between x and y or d of x comma y, this is less equal. Now we can write distance between xn and x here, because we know that by using symmetry we can write this plus distance between now xn and y. Now using 1 and 2 we write here distance between x and y, now this is less than epsilon by 2 plus epsilon by 2. Now epsilon by 2 plus epsilon by 2 is epsilon here, so therefore we write here distance between x and y is less than epsilon, but epsilon is arbitrary here, epsilon is very small, so this implies that here we have distance between x and y is equal to 0, so we get here x is equal to y, that is we get now in this case now here x is equal to y, it means that the sequence has unique limit. Now next theorem is about convergent sequence, that is every convergent sequence in a metric space is bounded, but before that we are going to see definition of bounded sequence here. Now definition of bounded sequence here, bounded sequence. Now remember that if the range of the sequence is the bounded set, or if range of the sequence forms a bounded set, then we in that case we say that that sequence is bounded. So definition is that in a metric space, a sequence is said to be bounded if the range of the sequence forms a bounded set here. Now for example, now if you take x is equal to r here and d of xy is equal to, now here absolute value of x minus y. Now if you consider now this sequence 1 upon n, where now n belongs to n, that is set of natural numbers. Okay, now here if we write now range of the sequence here, so we get now this set 1, 1 upon 2, 1 upon 3 and so on. So it means that here now all elements of this set, okay, actually here we strictly have this, so we have 0 is less than xn, now this is less equal n for all yes n belongs to n. So range of this sequence is the bounded set here, because we know that all the elements of this sequence lies between 0 and 1 here. Okay, now here now 0 is not member of this set, because now limit of this sequence is now 0 here. So we get that now range of this sequence is a bounded set here. So therefore this sequence is the bounded sequence in the set of real numbers here. So we are going to see this theorem. Now statement of the theorem is in a metric space every convergent sequence is bounded. Now proof of this theorem. So we consider a convergent sequence to prove this theorem. Now let xd be a metric space and xn, now this is the convergent sequence, be a convergent sequence in metric space X such that xn converges to X as n tends to infinity in matrix space X comma D. Okay, then now since this sequence is convergent, so therefore we have for each epsilon greater than 0, distance between xn and x is less than epsilon for all n greater than or equal to n, that is capital N. So now for that we taking here epsilon is equal to 1. Okay, then there exists a positive integer capital N such that, or n such that, now distance between xn and x is less than 1. Now here we have taken epsilon is equal to 1. So distance between xn and x is less than 1 for all n greater than or equal to n. Say this as 1. Okay, now since we want to show that now this sequence is bounded, now this is for all the terms when small n has value greater than or equal to n. It means that when we have small n is equal to capital N, then distance between xn and x is less than 1. Okay, when we have small n is equal to n plus 1, then distance between x suffix n plus 1 and x is less than 1. Now we take here r is equal to now maximum of r and distance between x and x. So here now taking r is equal to now maximum of 1, and here I am writing now this value. Okay, distance between x1 and x, then distance between x2 and x, and so on. We write here distance between now here xn minus 1 and x. So we can write here now taking maximum of 1, and here I am writing this distance between xn and x, where 1 is less equal n is less equal n minus 1 here, because we know that now distance between xn and x is less than 1 for all n greater than or equal to capital N. Okay, it means that now we write this when value of small n is greater than or equal to n. So that's why we are writing this. So we write here now distance between xn and xm. Now xn and xm are in terms of this sequence. So we write here this is less equal distance between xn and x plus distance between x and xm here. So therefore we write here distance between xn and xm. Now this is less equal. Now this distance is always less than or equal to r. So we write here r plus r, that is 2r for all m and n belongs to now set of natural numbers n. So therefore we write here distance between xn and xm. Now this is less equal now 2r for all m and n belongs to now this. So this tells us that now the range of the sequence is bounded by 2r, that is the diameter of the range of the sequence is bounded by 2r here. So this implies that the diameter of the range of the sequence is bounded by 2r. So therefore we get that every convergent sequence is bounded here. Now next is that, now remember that the property of convergence of a sequence in a metric space XD is not inherent in a sequence but depends on the space X and the metric is used. Okay, it means that the convergence depends on the metric, which metric you are going to use, and the metric function which you are going to use here. So first example is that now. So first example is now convergence depends on the space X. Now if you consider this space, that is X is equal to R, that is set of real numbers with usual metric, that is d of xy is equal to now mod of x minus y. Okay, now if you consider sequence xn, now xn is equal to 1 upon n plus 1, then remember now this sequence converges to 0 here. Okay, or this sequence has limit 0 and this belongs to x, that is this sequence is convergent in usual metric space. But if we take now this, if we take now capital X, that is capital X is equal to now this open interval 0 to 1 with the usual metric. Now I am taking the same sequence here. Now xn is equal to now 1 upon n plus 1, where n belongs to n. So now in this case, now this sequence has limit 0 here. Xn tends to 0 as n tends to infinity here. But now this value or this point is not member of this set, that is open interval 0 to 1, because 0 is not member of this set here. So it means that now we have same sequence here. Xn is equal to 1 upon n plus 1, and here we have again the same sequence. Xn is equal to 1 upon n plus 1. But now in this set, now x is equal to r, that is set of real numbers. Now this sequence is convergent, but in this set, now this sequence is not convergent here. So therefore convergence depends on the space x or that set. Now second is that convergence depends on the metric function, that is the function d. Now second is that convergence depends on the metric d used. Now here now we are taking x is equal to now C01, that is this is the space of continuous functions defined on closed bounded interval 0 to 1. Now consider the sequence xn here, where xn is equal to or xnt is equal to now e raised to minus nt, where n belongs to now n, that is set of natural numbers. Now this sequence with respect to metric d1 on C01, we write here d1 of xn comma 0. Now this sequence is convergent here, so integral from 0 to 1, we write here e raised to minus nt dt. So we write here now integral of this is e raised to minus nt upon minus n. Now limits are 0 and 1, so we interchange limits and we write here now 1 upon n into 1 minus e raised to minus n. Now remember that now this tends to 0 as n tends to infinity here. So therefore now this sequence is convergent. Now xn, now this sequence is convergent with respect to metric d1, okay, on this space or on this set here. But now if you take this set, okay, but if you take now this function d infinity, now d infinity of xn comma 0, which is now maximum value of mod of e raised to minus nt minus 0, where t belongs to now closed bounded interval 0 to 1. Now we write here now maximum value of e raised to minus nt, where this maximum value is taken over closed bounded interval 0 to 1 here. So t belongs to closed bounded interval 0 to 1. Now this value is 1 here. So it means that now as n tends to infinity here, now d infinity of xn comma 0 is equal to, we have now 1, which is not equal to 0, or this does not tends to 0 here. It means that now the same sequence here, now the same sequence xn is not convergent with respect to the metric d infinity on C01 here. Okay, so therefore now in convergence, in convergent sequences, or when we are studying convergence and all those, so in that case now the metric function is also important here. So thank you.